This time we go a little bit more into the details of how does the how does Flink compile its relational APIs. So in the talk before we saw a brief example on how stream SQL looks like, and this one is this talk is going to be how would such a query be actually translated into a Flink program. Yeah. So first of all, a little bit of motivation. So the data stream API is not for everyone. Everybody who's tried to write a streaming program knows it's not. The very simple things are not that hard. But if you want to do a little bit more complex things, you come to a point where you have to understand the streaming concepts pretty well. This includes state, time, windows, triggers, and a couple of other concepts, which are not so easily to wrap your head around. And of course, with the current API of Flink, you need to be a programmer, right? So you need to either implement the job in Java or in Scala. And a lot of this program logic goes into user-defined functions, and this is of course very good if you have complex logic to implement, because it's very expressive writing UDFs. But on the other hand, it's not so good for optimization, because all these UDFs are usually black box functions, so you don't really know what's happening inside. An optimizer does not know what it can do with these user-defined functions. And since you can't optimize it, it usually depends on the person who writes the code to tune the job to a point where it can reliably run in production. A very brief discussion of what are relational APIs. So relational APIs are usually declarative, which means the user says what he wants to have, and then the system computes it. So, and the system does not only compute it also decides how to compute it. So the user does not specify the implementation, and instead the system looks at the requirements, figures out how to execute the thing, and if it does a good job, it executes or computes the result in a very efficient way that would be very hard to obtain when writing the query manually. So if the system really knows what it needs to do, which is the case in declarative queries, then it can really go down and optimize for a lot of things that a user, if you would write the thing, would be first of all a lot of effort to implement, and second, the user would have to be very skilled to actually know about all these optimizations. So what is this talk about? So first, I'm going to talk a little bit about relational queries on streaming and batch data. What does it mean? What are the differences here? I give a brief introduction into the APIs of Flink, Flink's relational APIs. Then the core part of this talk is how does the translation really go? How is the translation done step by step? And finally, talk a little bit about what's the current state in Flink for these relational APIs, what is supported, what's not supported, and give an outlook about what can we do, or what do we plan to do, and what kind of improvements are coming up. So Flink, as you know, I guess, is a streaming and batch processor. And Flink also offers relational APIs for streaming and batch tables. So a relational query or query on a batch table basically means that the query reads a finite data set, processes the data, then the query terminates, and it produces a result of a fixed size. A query on a streaming table, on the other hand, reads an infinite data stream. It does not terminate. It starts computing and keeps on computing continuously as more data arrives, and it emits its result as a data stream. So the query is not executed multiple times, or it does not really terminate. It's like a standing query. And what we envision in Flink is to have the same syntax and same semantics for streaming and batch queries. So basically it shouldn't make a difference if you capture the stream, put it in a database, run your query on it, or whether you execute the query while the data is arriving. First about streaming queries. As I said before, implementing streaming applications on a lowest level is hard, and only few people have the skills to do that. At the same time, streaming technology is spreading out, and there's a talent gap. For more and more streams arrive, you want to do something with the data, but it's hard to find the people to actually do analytics on these streams that have this special skill set of knowing the streaming concepts and at the same time being a programmer. So also there is like a lack of open source systems that support SQL on parallel systems. Some systems do support a subset of SQL, but the state of the art is far away from where it could be. The most important thing here is that relational APIs will make stream processing much more accessible for a wider audience. So what do we need to actually do relational queries on streams? So as I said before in the other talk, you basically need, in order to obtain consistent results, you need event-time processing. So the result of the query might only depend on the data itself. So if there's like the result should not depend on the wall clock time of the machine that the query runs on. It should only depend on the data, on the time which is encoded in the records. Also, not all relational operators can be naively applied on a data stream. So for instance, if you try to compute an aggregate, like a count aggregate on a data stream, the stream is infinite. So you basically keep counting, and you always know there will be more data, but you can't really emit a count. So same applies for joins and set operations. So you kind of need to bound the input, need bounds on which you can evaluate your aggregation functions, or you can evaluate joins, and this is called windows. Sorting is restricted as well, so you cannot really sort a data stream. There are some restrictions here, but with some extensions and restrictions on API, we can actually make relational queries work also on streams. For batch queries, as I said, Flink does also support batch queries or relation queries on batch tables. So are we doing here yet another SQL on-a-dip solution? I'm afraid yes, but the primary goal for Flink is not really to compete with dedicated SQL engines like Hive or Drill or Impala. The goal for us is more like making the simple things simple. So you shouldn't be forced to write a UDF function to filter data, right? So you should just say, I want to filter on this field. You shouldn't. There are a lot of built-in SQL functions that you could use, and if you have access to these functions, you don't really need to implement a user-defined function. So, and it also gives you better integration to a lot of data sources, because if you know the semantics of a filter, or you're able to push it down into the data access. So you can push a filter into a Parquet table, or push a filter towards a database before you fetch the data, which is not so easy to do if you only implement your applications using user-defined functions. All right, so much for relational queries over batch and streams. Flink features actually two different APIs for relational processing. There is the table API, which is in Flink since version 0.0, and there is SQL, which was added with the latest release, Flink 1.1. At the moment, both APIs have equivalent feature set. We'll also see in a moment why that is. And both APIs can actually also be mixed with each other. And both are also tightly integrated with the data stream and dataset API. So if there is something that you cannot really express in the table API or in SQL, you can always basically go to the more general data stream or dataset API. The table API is an API which is basically follows the language integrated query style. So queries are not embedded as strings into your program. You know that when you're writing a SQL query in your Java application, you usually put it in a string, and it's kind of like decoupled from your program, right? With LINQ-style APIs, it's a bit different. So these are actually like first-class members of the programming environment. How that looks, we'll see that in the next slide. The table API is centered around so-called table objects. So you have a table object which represents a data set or a data stream, depending on how the table was derived. And then you apply functions on this table, like you say filter, you apply a filter predicate, and the result of this is, of course, another table. And so you go on, apply different functions, multiple functions on your table, and in the end, the result is a table. The table API is available in Java and Scala, and it offers methods to convert a data set or data stream into a table and also back. So this is how it looks like. This is a table API for a streaming data source. We see here on top, we have a sensor data, which is a data stream of string, long, and double. This is somehow obtained. We can just read it from Kafka or did some pre-processing with it. It doesn't really matter. So the only thing that matters is it is a data stream here. And this data stream here, we can easily convert into a table. So we see a sensor table here. And this is done by simply saying this sensor data to table. And then we provide here the attribute names that we want the fields of this data stream to have. So we say location, which is maps to the string field here, time to the long field, and temperature in Fahrenheit to the double field. And then we can define our table API query on this table. We have the sensor table. First of all, we say group by location. So we group the table by location. We then say, let's compute a window here. This is a tumbling window over 1 day on a runtime attribute, which is like an additional metadata attribute to the table. And we give this window also a name with the alias here, which is just W. And then we have our window defined over the query. It's like a partitioned window. We have each hour, we have a window for each location for 1 hour. And on each of these windows, we apply aggregation function here, which is we compute the average of the temperature in Fahrenheit, and then convert it to Celsius. We also say W start, which is basically give me the start time of this window, and we also want to keep the partition key, like the location on which we set the group by. And finally, we say we apply another filter here, where we say location should be like room something. So we're only interested in the average temperature in certain rooms. So this is how this table API looks like. The SQL API of Flink follows standard SQL. So we're using the SQL parser from Calcite, which follows standard SQL. Queries are embedded as strings into programs, and we somehow, since we don't, we kind of like since the query is more or less detached from the rest of the program, we somehow, when we say select from some table, this from this some table needs to be registered somewhere, right? So this API basically requires that you have registered the tables that you want to query with SQL in a special environment. And when a query is evaluated, it returns a table object, which means you have a nice integration with the table API. So if you want to, you can then apply another table API expression on top of the query that you computed. How does it look like? So here in the top there is a lot of boilerplate code. So we define here an external table from a CSV file. Here so we say, okay, this is the path to the data. We define the names of the column, location, day, and temperature. It's an array of a string, and a double, and then we just we have this. This is a so-called table source in Flink, which is basically a reference to an external table. So this could also be a reference table in a JDBC database. It could also be could also reference data in a Parquet file or whatever. So this is it's a pretty generic interface. And this sensor table we now register as in a table environment. Say, okay, register table source, and we give it a name, sensor data, and then in the following SQL query here, we just refer to the sensor data table, and then we more or less compute the same. Or we then can execute a regular SQL query on this table here. We just say location should be like room. We group by day and location here. So this is a batch example. We're not doing the doing the windowing in here because it's a batch example. And then we select the day, the location, and compute the average of the temperature, which is converted to Celsius. This is how SQL currently looks like in Flink. So the table here, so the table, where this table comes from, you don't need to go through this external table source interface. You could also create a table just like here, have a regular data stream or data set, convert it to a table, and then register the table or the data set directly as a table to query with SQL. All right, so much for the APIs and how they look like. So we have now two different APIs. We have the SQL, we have table API. We have two backends to compute stuff on, the data stream and the data set backends. So does that mean we have like 4 different translation paths? Of course not. We thought a little bit about it, and we came up with a nice design, I would say, which I'm walking through in the following. So you see, we can already see here in the center part there is a lot of light blue boxes, which is Apache Calcite. What is Apache Calcite? So Apache Calcite is also Apache project, of course, and it provides a SQL parser and optimizer framework, among other things. There's also like JDBC drivers, and it also validates, of course, the SQL query. So it's a lot of things centered around what you need when you deal with SQL. Calcite is used by many projects, so including Drill, Hive, Kylin cascading, and since Flink 1.1, also in Flink. And the Calcite community is putting streaming SQL quite prominent on their agenda. So, the Calcite community thinks of streaming SQL as an extension to standard SQL. So we don't want to invent a new SQL-like language, but instead keep standard SQL and do a few additions to it. In some cases, also restrictions. So there are some things which you can do on a batch table. But if you want to apply the same query on a streaming table, which wouldn't work. And Julian gave a talk about streaming SQL this morning, so he's also here. All right. So how does our architecture look like? We have table API queries here. We have SQL queries here. Both are translated to the same logical representation, which is a Calcite representation. It then goes into the Calcite optimizer and is optimized with rules depending on the execution backend. And finally, the resulting optimized plans are translated into a data set or a data stream program. So this is like more or less plain, it's translated in the core APIs of Flink. So it looks like a regular Flink data set or data stream program in the end. There are quite a couple of components here. First of all, there's a catalog component. We need to register all tables in this catalog for parsing, validation, and optimization. So also, whenever you translate a data set into a table, and you don't need to explicitly register it in the catalog, but we will do it for you. So you can if you want to go fast, you just say dataset to table, and then we register this table as an internal name into this catalog. So every table that you create from some external representation, be it a dataset, data stream, or data source, is somehow registered in this catalog. Then, as a next step, or looking at the table API representation, each of these API calls, when we say like we have table and then say table select or table where, each of these calls is translated into a logical operator and is immediately validated. So we immediately check when you say select this and this and this column, it immediately checks are these and these columns actually present in the table that we applied this this operator on. All these operators that are generated, this is like still a Flink internal representation. All these operators are composed in a tree of operators, so which is very common for SQL queries or for relational queries. And before the optimization happens, this tree of logical Flink operators is translated into a Calcite logical plan. So basically this representation here. And this happens mostly with internal tooling from Calcite. So Calcite offers a so-called rel builder to easily compose relational queries in this logical tree representation. How does it look like? So we have this query that we had before. We have the sensor table here, which is like the can be thought of as a scan operator. So because we were accessing this sensor table here, which is translated into a so-called catalog node here. We have then the group by window select, which is translated into a logical aggregate, into a window aggregate operator. So also multiple of these, depending on the operator, are translated into the same operator, into the same logical operator here. We have a projection here to do this projection here, or this computation of the on the computed average, and finally a filter here to apply the last filter. And finally, when, as I said, before we go to the optimization phase, this internal Flink representation is translated into the logical Calcite representation. Coming from the other side, coming from SQL, we're pretty lazy. We let basically Calcite do all the work here. So the SQL query goes into the SQL parser as it is. It is validated against the table that we registered before. All that happens basically within Calcite, and in the end, Calcite also produces this logical tree, logical representation. So we're not touching this thing at all at this point. So you basically see here. So we have this query here. It goes through the parser, the validator, and what comes out is this logical plan. And what we basically end up with is we have the same logical representation for the table API or the SQL API. So it really, depending on what kind of queries you write on both sides, you get the same result in the end. Next step, what happens? So whenever you're now trying to convert a table into a data set or a data stream, this is when we're basically when the optimizer needs to take action. So what happens then is we basically give this logical plan to the optimizer. We use Calcite's volcano-style optimizer. So this optimizer applies. It's a rule-based planner, which basically just applies transformations on the logical representation. So you transform one tree into another tree, and it makes cost-based plan choices. So it basically looks at whenever it does a transformation, does this yield a better plan or with lower cost, yes or no? And then based on the estimated cost, it decides whether to keep this plan or not. So it's classic volcano-style optimizer. Calcite provides a lot of optimization rules, mostly for the batch part. But some of the rules do of course also apply in the streaming part. So for instance, like pushing down filters or merging filters and projections. So a lot of these things can be applied in both APIs. And we also provide custom rules in order to transform these logical nodes, this logical representation, into the respective representation that we need to translate the data stream or data set program for. So when we optimize a query for on a streaming table, we're using the so-called data stream rules, to which then convert Calcite's logical nodes into Flink's data stream nodes. And the same goes for the dataset nodes. So this looks like this. So this is like the original plan, which came out of a table API definition. We then optimize this plan here. What it basically does, it takes this projection and the filter and pushes it in front of the window aggregate. It also merges the two of these, logical project and logical filter, into logical calc, which is like a you can think of it kind of like a flat map function. So it can do filtering. It can do it can also do transformations. Right, and then this is like the best plan that the optimizer finds, and then this plan is transformed into a data stream plan. So here, see it's more or less like a one-to-one transformation. So each of these logical operators is translated into a data stream equivalent plan. So this is not yet like a data stream program, but it's a plan representation of this program. So because what happens next is we have to translate this Flink plan into a Flink program. And these Flink nodes are implemented in a way that they recursively translate themselves. So they basically go back recursively on their inputs, let the inputs translate, first the inputs translate them, and then recursively the data stream program is composed. Of course, we somehow need to translate like expressions, SQL expressions into a Flink code, and this happens via code generation. So the user functions that we, for instance, have to give into a flatmap function to do for filtering or for computing projections are code generated. So this we generate code for expressions, conditions, for built-in SQL functions. So all of this is basically going through code generation. This code is generated as a string, embedded in a Flink operator, and then shipped to the cluster. And on the cluster, it is compiled. And for that, we're using the Janino compiler framework. So this is like a it's a Java compiler which automatically loads the general classes into the class loader. And of course, batch and stream queries here share the same code generation logic. So we're not doing duplicate work here either. So how does it look like? It doesn't look like not very fancy here. So we have this data stream scan, which basically, depending on how this initial table was generated. So in the initial example, we saw that this, in the initial example for the table API, we saw that we just took a regular data stream and converted it into a table, right? So this table is backed by an actual data stream object. So all we have to do is we just use this data stream object, and then we apply a flatmap function on this data stream object, where the function is where the user function is code generated, and then we apply a window aggregate on this on the result of the flat map. And then at the end we end up with a data stream object, which then can be either used in another table query, or we can just continue processing it with all the regular data stream operators that we have at hand. So you can basically think of this as some kind of a nice way to generate data stream programs with code generated user functions. And the whole thing is then also nicely embedded into an existing program. So here the purple nodes, you can, as an example, could be generated via the table API, and then you can have these nodes which are processed with the regular data stream API. One thing to add here is when you compile programs to the batch representation, this still goes through Flink's dataset optimizer. So you might know Flink's batch API has an optimizer internally which does optimizations such as it does not optimize the order of operators such as Calcite operator does, but it, for instance, it optimizes what kind of physical execution strategies are used for a join, for instance, whether it uses a sort merge strategy or a hash join strategy, whether it uses a broadcast join or a repartition join. So all these things are in this level basically decided upon by the Flink's dataset optimizer. And then the whole program as a whole is executed just as one thing. So we have the code generated parts here from the table API and the parts over the UDFs you wrote yourself. So all of this is executed in one batch. All right. So this is basically how the translation works. The current state is Flink 1.1 features table API and SQL. Streaming SQL and table API supports in this version selection, projection, and union. So what I've shown you before here, like the window aggregations, are not supported in the latest release. So this is a work in progress, but it's actually work in progress. So we have a working prototype of this. So the support for the batch SQL part is more extensive. So it's selection, projection, sort, inert, outer, equi joins, and the set operations. Quite a few of the SQL functions are also supported. So what's coming up for relational queries on streams in Flink? First of all, and most importantly, streaming aggregates. So I said we are working on these streaming aggregates on the table API. So this is for us a starting point to get the programming logic and also the translation part going. For streaming SQL, what is basically like missing is supporting Calcite's query parser. So the Calcite community is actually working on that. So they have an effort to support tumbling windows and what we call session windows. The Calcite community calls it hopping windows, and also sliding, no session windows. So there's an effort to have nice expressions for that in the group by clause. And we are coordinating with the Calcite community to also get this feature into Flink. Of course, joins are also like a requirement by many people. So this is would then be the next step. So there are different kinds of joins. You can think of joining two streams, like high volume streams, where you basically need to define your join in terms of a window. You can also think there are other applications where you're like joining against a static table or slowly updating a stream, which is kind of like the easier scenario here. And of course, we also want to add more table sources and sinks. So these table sources and sinks are basically shortcuts to not go through the data set or data stream API. So if you've seen with this CSV table, so if you basically can define this CSV table like an external thing and have it pre-registered in your data in your environment, then you can immediately start querying this registered table using SQL. General improvements for basically both sides, batch and streaming, are extending the code generation. So far, we're using code generation mostly to generate for expressions. We're not using it yet for data types. So we have like a very generic data model for this, which can be optimized in terms of efficiency. That also means that we would generate our own serializing comparators for that. Aggregation functions are currently also not code generated. Of course, support for more SQL functions and user-defined functions, and standalone SQL client. So as what I said before, so some environment where you have like some tables pre-registered, and you can simply start querying these tables, maybe like batch tables or tables defined over a Kafka topic, for instance. All right, so there's still quite a bit of work to do in this area. New operations, so especially in the streaming side, and features, performance improvements, tooling like a standalone client, and integration with other data sources like Paket input format or HBase or whatever. So there's so many data stores out there that we could use. If you're interested in that, just get in touch and talk to us. And this brings me to my last slide. Just a summary. Flink has these two APIs, Table API and SQL. Both go through the same optimization path. So we're bringing it down to a common representation as a SQL plan, as a Calcite plan. We use code generation to generate the functions to have efficient code, and the execution happens basically as regular data stream and data set programs, which also means whenever these get improved, the Table API and SQL also benefit automatically from that. All right, and in the end, we hope that we can make with these relational expression or relational APIs on top of streams, we make this more or less maybe not for everyone, but for a much broader audience. All right, thanks.
I missed the beginning of the talk. Did you cover why we have Table API at all? Like, do we really need Table API and SQL API as separate ones? Like, is there any reason to use Table API over SQL?
So the question is, why would you use Table API?
Yeah, versus SQL.
Well, first of all, some people like this language integrated style better than just putting a string into a program. It also gives well, at least us, a little bit more flexibility in terms of how can we actually design this API. So there are certain things where we have to, for instance, like how we had in the previous talk, there was a question, how are we dealing with lateness? So, of course, we have to see what kind of answers we find in the SQL part for that. So what we kind of like envision also for this Table API is to since a lot of things are like code generated, in the long run, when we like also start adding user-defined functions like lining into this could also yield in the end something like a data stream API 2.0, right? So you have like your predefined you have your predefined data model. You can also express user-defined functions in there, and you have like a few nice declarative primitives for which we can generate very efficient code, right?
So does it mean that Table API will always be superset of SQL API?
Not necessarily. So for instance, right now they're equivalent. So it's hard to tell in which direction this goes right now. So as I said before, we basically started with the table API, and the table API was there before we started our SQL effort, and we wanted to keep it. So that's more or less how these things came together. Yeah.
So thanks for the talk, very interesting. So my question would be, since you have basically two independent optimizers, like the Flink optimizer, right, and the Calcite optimizer. So my understanding is that Flink's task basically is to provide the Calcite optimizer with both like statistics and also cost functions. And since you don't actually know the physical implementations of operators, how are you going to provision cost functions for these, like for instance, for the join?
Yeah, that's a good question. Actually, so far we are not really leveraging statistics at all. So as you've seen, we can generate like a table can be created from any data set, so we don't really know where it comes from. It can come directly from a data source, like from a file. It can also go through some very expensive or unpredictable operations, so for which we would not be able to compute statistics. So right now, we basically decided to not do any join optimization yet. We say, okay, in the current version, we just keep the join order that the user specifies. In the long run, of course, once we have better integration with external data sources, we can also leverage more statistics. And the Flink optimizer, like the Flink data set optimizer, accepts a lot of optimization. And so what we still can do is let the Calcite optimizer do all the planning, like also choose physical strategies, and then fix the strategy when we pass the plan to the Flink optimizer. And then the Flink optimizer won't do a lot.
Hi, thanks for the talk. Just one question. So maybe it's more of a clarification need that I have. So let's say you define a table on a data stream. So does that table then live somewhere within Flink and can be queried by any Flink application, or is the query that you're running on that table, closely tied to the definition of the table? So does it have to be in the same application?
So the table is not really like a physical entity. It's more like what this streaming table gives you is more like it just gives you a schema for how the data that comes with the stream looks like. And the query is constantly running and producing a data stream. So it doesn't, of course, it keeps some state. If you define a window, it has to accumulate the data in the window. But this state is not really accessible from the outside. With queryable state, there might be ways to expose this data. But the way to think about it is basically these relational APIs, they just transform one stream into another stream.
Okay.
So of course, it's a very interesting idea. Also, Julian pointed that out this morning in this talk when he talked about this pie chart problem. How can you? The question is, if you have a data stream, can you somehow bring this data stream into a view, like a maintained materialized view, on which you can then run batch queries, also just regular batch queries. So this is something that we kind of like have in the back of our minds, but we haven't clearly defined yet. And yeah. Okay,
thank you very much. Just one more question. So, in a lot of cases, the source of a data stream will be Kafka. So, Kafka, they brought out a library, Kafka Streams, recently. So, I don't know, is there anything that can be compared between Kafka Streams and your work on Table API and SQL on Flink? Or do they just coexist and don't necessarily try to accomplish the same things? Because it seems like it a bit,
So Kafka Streams is more designed like a library which you can embed in your application, right? So this thing, the Flink's relational APIs are in the end not a lot more than a nice way or a declarative way to specify data stream programs, right? These programs, have run on dedicated stream processing software, like on dedicated workers in a data center. It's yeah. So it's from an architectural point of view, it's very different. So usually like Kafka Streams, from my understanding, is more designed towards serving like a micro architecture, microservice architecture kind of frameworks. Whereas we're trying to do high throughput transformations in data streams and aggregations.
Thank you. My question is about multi-windowing queries. If you, for example, need you have two sources with two different windows, or you have to process a window downstream of another window. What do you think about the syntax? Or maybe I can also SQL syntax, or
so in SQL, I mean, you would go like for either nested queries, or you would define a view on the first window, or the result on the first window, and then basically define the next query as So that's the nice thing about SQL. It's really composable, right?
Oh yes, I didn't.
And with the table API, it would be quite similar. You would just say group by window select. The select would then basically be like the contain the aggregation that you want to do in the window, and then you would say again group by window select for the next window.
Okay, so it will come straightforward.
Yes.
From,
yes.
Okay.
Yeah.
Okay. Thank you.
If you want to do something like compute a 10-day moving average and a 50-day moving average, you can do that with an over clause in SQL. You can do that in one site segment. You don't need to test it because you keep both simultaneously. I don't know whether Flink can do that. I don't know whether SQL can express you can compute multiple moving average functions
Yeah.
over different window, different function, and it's simultaneously the same statements.
Yeah. So we also want to support that. Yeah. So it's. Yeah. Thanks.